The real thing in a quantum theory, a path integral quantum theory, is a statement, yes or no, to every possible question. Does such and such an event happen? And in the world, it either happens or it doesn't happen. And the list of all those answers, yes, no, yes, no, 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 yes, no, to all the possible, for every event, you can ask the question, does this event happen or does it or not? And then the answer to all those questions, that's the world. That's the... We like to joke that it's a Wittgensteinian answer. It's everything that is the case.
Hello, this is Robinson Erhardt here with the introduction to Robinson's podcast 156. I've actually recorded like 190 something episodes at this point. I mean, a bunch never got aired because they were very early ones, but it's crazy that I've almost done 200 of these and I feel like I still have no idea what I'm doing. Is this even real? I don't know. Anyway, this episode is with Fay Dowker, who is professor of theoretical physics at Imperial College London, where, quite broadly, because she's worked on lots of things, she works on quantum gravity, but more particularly focuses now on an approach called causal set theory. And causal set theory is quite new to me. And as I mentioned in the episode, I learned about it from Lee Smolin, and I think somewhere else that's now escaping me, but I'm reading some of Stephen Wolfram's work right now, and he also refers to causal set theory. But like string theory, it is a theory of quantum gravity, and it takes the world to be fundamentally quantum mechanical. But what's unique about causal set theory is that it takes the most basic pieces of the universe to be discrete atoms of space-time. So it chucks the continuity of space out the window, which I personally find quite appealing. And we start off by discussing Fay's studies at Cambridge with the illustrious Stephen Hawking, who was her advisor, and also their work on wormholes, which is quite cool. And then we get into the basics of causal set theory as an approach to quantum gravity, and we situate it with respect to black holes, as often I find interesting to be the case with quantum gravity, in that it's a great way, black holes are a great way to introduce the various theories. So Fay is also a faculty member at the John Bell Institute for the Foundations of Physics, which, as you know, are many the other guests on the show. Most recently, Tim Maudlin, who's the founder, and the next episode is also a faculty member at the John Bell Institute. But if you're interested in physics, the foundations of physics, which you should be, please check out the John Bell Institute, which is devoted to providing a home for research and education in this area. And I've donated, and any donations are extremely helpful at this point in their life as they're trying to secure their forever home in Hvar, Croatia. So last thing I will mention is this new t-shirt you've totally been eyeing, which says Robinson's Podcast with Pins the Podcat. This is Pins the Podcat. And it's available at robinsonsfashionempire.com, which you can also just find by going to robinsonerhardt.com. It is the third shirt in this growing, soon to be behemoth fashion empire. So comments, likes, subscribes, reviews, all these things are endlessly appreciated. And now, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with Fay. I saw that you did your graduate work at Cambridge with Stephen Hawking, and a few weeks ago, I actually spoke with another of Hawking's students, Thomas Hertog, about their work on quantum cosmology. He recently had a book that came out all about this. But since I believe, and Wikipedia has gotten me in trouble on a couple of occasions, that you did your dissertation on a different topic, and that's wormholes, I thought we might start with that since they've never come up on the show before. And most people are familiar with wormholes from science fiction books and movies, but where do they actually arise as a real tractable problem to work on in physics?
There are two types of wormhole. It's slightly confusing because you draw the same picture on a piece of paper to illustrate them both, but they differ in dimension. So one sort of wormhole is a wormhole in space, which is it connects one region of space. It's like a shortcut from one region of space to another region of space. You just go down the wormhole in one end and you pop out somewhere else in space, somewhere else. And those, it's interesting that the first instance of such a wormhole is already there, inherent in the space-time that we use to describe black holes. So, and there the wormhole goes by the rather grand sounding title of Einstein-Rosen bridge. And it connects not two regions in the same space, but two different copies of space. So one universe and another universe, they're joined by this so-called Einstein-Rosen bridge. And the interesting thing there is that in that space-time, it's the Schwarzschild space-time. It's the space-time that describes the simplest possible black hole, one with just mass and no other attributes. It's not traversable, so it's there in the description of the space-time. There's this bridge, but if you try and go down it, then it pinches off, and you actually hit the singularity before you're able to go through into the other universe. So that's a non-traversable wormhole. And people have speculated about whether there are traversable wormholes in the world and how you could keep the wormhole open long enough for you to actually get through it from one end to the other end. And people a lot of work has gone into doing that. And I would say that probably, you'd need a certain slightly exotic sort of quantum matter in order to do that. And it's not, I would say it's still an open question whether such things exist in our real universe. So that's one type of wormhole. So the second type of wormhole are wormholes in space-time. So they arise, well, speculatively, Stephen was interested in wormholes because he thought that might be what was happening when a black hole forms and then evaporates. And people asked the question, well, he posed the question, what happens to the stuff that falls in? And one speculative answer to that he proposed is that, well, a little baby universe pinches off our universe and goes off and carries the stuff that fell into the black hole away with it. And that process of this baby universe pinching off, if you look at it in space-time, so if you look at the whole history of that process, it looks like a wormhole. It's not the same dimensionality of wormhole as the Einstein-Rosen bridge, but the picture that you draw is looks the same, but it's just one dimension higher, one dimension up. And that proposal of whether or not this could help resolve the so-called black hole information loss paradox or puzzle was what I was working on for my PhD.
For the Einstein-Rosen bridge, is that the same Rosen of Einstein-Podolsky-Rosen? Because that paper has come up a number of times on the show.
Yeah, so there's a sort of almost a joke kind of, but not a joke because serious people take it seriously, connection between those things because, and there's even a title of a paper, EPR, as in Einstein-Podolsky-Rosen, equals ER, as in Einstein-Rosen bridge. So that somehow these wormholes in space could have something to say or something to do with the non-locality of physics as revealed by the EPR type correlation. So I'm hugely skeptical of that, but that is a thing.
Yeah, that's interesting. If two particles separated by some great distance interacted with one another through an Einstein-Rosen bridge, would that be considered a local interaction because nothing's moving faster than the speed of light, even though they're obviously quite distant?
What was it? That it's semantics. I mean, the term local, both terms, local and causal, are so overused and used differently in different contexts, and different people can mean different things by local, and the same person can mean different things by local depending on the time of day or what they had for breakfast. So it's
sure. I guess I just had the sense that Einstein wouldn't qualify as the sort of spooky action at a distance that he really despised if there were this wormhole connecting them and nothing was moving faster than the speed of light.
I don't know. I don't know what he would have thought about that actually. So yeah, hard to say.
Yeah, I probably shouldn't be supposing I have any insight into his thinking. But one last question about these two varieties of wormhole. So the Einstein-Rosen bridge and then the baby universe pinching off. Maybe this is presaging our talk about causal sets as a theory of quantum gravity. But is the Einstein-Rosen bridge something that arises just within general relativity, or does it also importantly involve quantum mechanics? Because you did mention that I think you said this, making a traversable wormhole would require some sort of exotic quantum matter.
Yeah. I think largely discussions of Einstein-Rosen bridges, those sorts of wormholes in space, they take place within what people usually call semi-classical gravity, meaning that space-time is supposed to be in this regime well described by a differentiable manifold with a Lorentzian metric, so sort of a la GR. And then matter is allowed to be quantum. And you may or may not consider back reaction from the quantum matter onto the space-time. And if you want to keep a wormhole apart, traversable, then you would have to consider the back reaction of this rather exotic matter with negative energy. You'd have to consider the interaction between that quantum matter and the semi-classical, the differentiable manifold structure of space-time. So that's different from what people mean when they say full quantum gravity, where there are sort of fully quantum effects of space-time itself that can't be described by a differentiable manifold with a Lorentzian metric. So yeah, so the sort of baby universe type wormholes, they're described they arise in descriptions of the full theory or approaches to quantum gravity which are tackling the full problem of quantum gravity rather than just space-time as we know it, but reacting to behaving as if the matter in it is quantum. So, but there's overlap, and some people who are thinking about the baby universe type wormholes are thinking about them as in some sense semi-classical. So that's not a hard and fast rule, but that typically, yeah.
That does make sense to me, though, with regard to the second type of wormhole, the baby universe pinching wormhole, just because, as again, this is getting ahead of ourselves, but black holes and the singularities at the center of black holes are one of the places in the universe where the tension between quantum mechanics and general relativity becomes most salient and apparent, and it's where the theories sort of break down. But before we get to that, Stephen also, one last thing about Hawking. I mean, he was very famous for saying and writing that philosophy is dead. And what's so interesting about that for the purposes of our conversation is that, as I mentioned before we spoke, I found your work through Lee Smolin. I'm not sure if it was his book, Einstein's Unfinished Revolution, or The Singular Universe and the Reality of Time, but causal set theory might have come up in both of them. But then also through Tim Maudlin, who I've spoken with. He's a friend and we've spoken many times on the show. And I saw that you were part of the John Bell Institute for the Foundations of Physics. And the point of that was that I found your work largely, I think, on philosophical grounds. So before I ask about your relationship to the foundations of quantum mechanics and philosophy of physics, what do you make of Stephen's views on philosophy?
Stephen liked to be provocative. I'm sure. I never discussed this particular thing with him, whether to challenge him about it. But I mean, while I was a PhD student in Cambridge, I was thinking of, when you wrote your email, it prompted me to think back about when I was a PhD student. So when I was in Cambridge, I remember I did not learn anything about the Bell inequalities, about quantum contextuality, non-locality, or any of the debates around these foundational issues in quantum theory from my physics degree or courses or anything like that. I found them out because I went to a meeting called the Sigma Club, which was run by Professor Michael Redhead of the Department of History and Philosophy of Science in Cambridge. And I can't remember how often they were, but they were marvelous talks and then marvelous afternoon teas. And that's where I learnt about these more foundational aspects of physics from the philosophers of physics. So yeah, that's my first personal engagement with philosophers, was that I learnt stuff that I ought to have known as a physicist but didn't. I've never discussed that with Stephen, and it's obvious that he has philosophical views. You can't not have philosophical views if you're a cosmologist like him, and particularly a quantum cosmologist like him. So yeah, I don't know what to make of his pronouncements. Maybe he just didn't talk to I don't know. It's hard to know. Yeah, but he didn't come to the Sigma Club meetings, although he would have loved them. I think if he'd gone, he would have enjoyed them immensely.
When you say that he obviously had philosophical views because of the nature of his work in quantum cosmology, is there anything in particular that comes to mind?
Yeah, I suppose he I mean, his debates with Roger Penrose, which were there was a series of interlocking lectures that he and Roger gave in, I'm trying to remember, is it 1989, something like that. And they're written up, so I think that volume may be called The Nature of Space and Time or something like that. But they gave alternate lectures, and then they had sort of responses to each other in the final lectures, and they were all about philosophy of I think that, well, certainly of quantum theory, and they have a sort of distinct and not exactly opposing views, but certainly, not exactly contradictory views, but perhaps alternative views about quantum theory, and they're philosophically based. I think they're. So yeah, that I suppose I'd point to that if you were to ask what his philosophical views are.
Well, the last thing I'll ask before we move on to causal sets, which I know is the main focus of your work, is how is philosophy relevant to that work in causal sets? Because I know that, you collaborate with philosophers, you're a fellow of the JBI, as I mentioned, but also your work in so much as it connects to questions of consciousness or causation or the metaphysics of time, it's already deeply philosophical.
Yeah, I suppose I can't avoid it. So that's even if I wanted to, which I don't. But I suppose my view is now, quantum gravity is it's such a difficult problem, partly because it's so conceptual. We're struggling to find the right concepts to use in building this theory, and that conceptual work is, there's no clear distinction. There's no real distinction between philosophy and physics, just like there's no real distinction between physics and chemistry, and there's no real distinction between chemistry and biology. They're arbitrary divisions that we put up because we just can't house everyone in the same building. So you just have to label people one thing or another just for practical reasons, but there's no real boundary, there's no real division. So, but I suppose in quantum gravity, because we don't know what the right concepts are, we're struggling at that sort of conceptual level. It's sort of inherently philosophical insofar as you could say what philosophy is, which is to try to define concepts and make them meaningful, connect them with our experience. So I talking to philosophers just as I find stimulating and helpful. And I think, Einstein was known as, a philosopher scientist, and we as a community could be a community of philosopher scientists. We don't all need to be both philosophers and physicists, but if we have expertise from both sides, then that can only be good and fruitful, helpful.
Mm-hmm. Well, let me make a few comments. This idea that you just put forth, that there are no real divisions between philosophy and physics, that's something that's definitely come up on the show before. One of my early episodes with David Albert, who you also will know from the JBI, we talked at length. He explained to me at length how there are no divisions. It's really like a continuum from maybe questions at the foundations of physics on the far side, and then maybe applied physics on the other. And you have philosophy of physics, quantum mechanics, all sorts of things, plasma physics. They're all just in there somewhere. And something that Tim Monlin has pointed out is that it's really just a sociological fluke that these questions at the foundations of physics have been relegated to philosophy departments. They would be just at home, if not more at home, in a physics department. But you also mentioned Einstein, and I've read in a number of places that he was committed to this idea of the universe being static because of a philosophical prejudice. And in this case, philosophy wasn't that helpful in that it prevented his recognition of expansion, which he might have done much earlier. But moving on now toward causal sets. While I know there are numerous candidates for theories of quantum gravity, I mentioned Lee Smolin. We just spoke yesterday, though we didn't really touch on loop quantum gravity at all. But the only one I've gone into in depth on the show so far is M theory, or string theory as it's more colloquially known. And I know that you've worked in string theory as well, but it should at this point be generally understood by our listeners that one of the critical difficulties in reconciling quantum mechanics with gravity is that in general relativity, the geometry of space-time is smooth and continuous, whereas in quantum mechanics, on the smallest scales, even space is violently jittery and indeterminate. And I'm wondering if you think that's a good characterization of where one of the major problems lies, or do you have a way you prefer to intuitively motivate the need for a theory of quantum gravity?
I think that's one way to approach it. That you can take what we know about how a quantum theory, say a quantum field theory, behaves, and apply it to the gravitational field, and just heuristically do a back of the envelope calculation about quantum fluctuations, and see that as you try to as you make the region that you're interested in smaller and smaller, then the fluctuations become larger compared to the background field, and then eventually they become as large as the background field. But because the background field is space-time itself, it seems like that picture of there being smooth space-time with stuff in it itself breaks down. So I think that heuristic is something that I don't know anyone who disagrees with that idea, that or anyone who accepts that one should think about quantum gravity at all. I mean, there are people who think maybe it's either premature, or maybe gravity space-time could be random and rough, but it doesn't need to be quantum. That's another possibility. But but then that raises the question: what should we replace space-time, the description of space-time with at that scale? So if it's breaking down, and we don't just want to say, we throw up our hands and say, well, physics breaks down, and we can't answer the sorts of questions we want to answer, like the one you raised, which is what happens at the singularity of a black hole. We either just say, well, there are no answers to those questions, or we say we have to pursue the question of what do we describe space-time with? What is it like in those regimes where the quantum fluctuations are so wild that the differential manifold is not a good description? So that's a good question to start with. What's the fundamental? What's the substructure of space-time? What is it? What is what's the analog of kinetic theory of ideal gases for space-time? So we have the continuum description at large scales. What does it look like on the smallest scales? That's a fair Yeah,
Good.
fair question to start with.
Well, toward answering this question that you just posed, I mean, what do you replace it with, or what should we replace it with? You write, I think it's in your paper, Introduction to Causal Sets and Their Phenomenology, that we can't just deduce a theory of quantum gravity from quantum theory and relativity. What we have to do is take and this is where I quote you, a creative leap. And I'm wondering if there are any particular intuitions that you have, or that one has, about what's missing from quantum theory and relativity, maybe about what space should be like at these very small scales, that point you in the direction of the leap, I'll be poetic, through the unknown to causal sets.
Yeah, I'm going to try and make it sound like as small of a leap as possible. So, but it's obviously still a leap. So the two ingredients that go into the proposal, the particular proposal that's causal sets, that causal set theory makes for this replacement for the smooth manifold structure, are discreteness, or one could go even further than discreteness, and say finiteness of physical reality, and order as being the fundamental ingredient. So finiteness, that has many good things to recommend it. Some of which are philosophical, and some of which are sort of philosophical going back, until as early as one can go, that we have records of people thinking about the nature of the world. So it's a repudiation of physical infinity. Right? So
are you thinking about Einstein and Zeno? I mean, sorry, Aristotle and Zeno.
Yes. Yeah, certainly. And an order, that's also, I think, although I've never done a philosophical study of it, that's a concept which is I think very primitive. It's not, and probably has a long history. But in general relativity, it has a very special status, because in general relativity we have the space-time causal order, or the light cone structure. And if you open a GR textbook, there are loads and loads of pictures of which we call Penrose diagrams, or Carter-Penrose diagrams, or conformal diagrams, which are of the light cone structure, the causal structure. It tells you what points of space-time can causally influence what other, what stuff that's happening over here causally influence stuff that's happening over there. And to answer those questions, you have to know their light cone structure. Black holes are defined in terms of the causal structure, the causal order. And many theorems that we prove in classical general relativity, including the ones that Roger was awarded the Nobel Prize for, they're all what you might call global causal analysis. So this causal order is right at the heart of the physics of GR. And if you put those two things together, and it's not that big a step to come up with a causal set, because a causal set simply is a discrete order. That's what it is. I mean, that's a mathematical definition. Discrete order. It is a causal set. They're synonymous in mathematics. So yeah. So it is a leap, and the leap is A, discreteness, and B, the order is the more fundamental of all the continuum concepts in GR. The concept of order is the most fundamental. It's the one that is going to survive in the deep theory. So, and that just automatically gives you a causal set.
Well, now we get to dig into this in depth. The first thing, though, that I was just hoping for clarification of was this distinction that you draw between finiteness and discreteness. As, I mean, well, one, just the distinction, and then why one might be more primitive than the other. Could you elaborate on just what you meant by that?
Yeah. So, in the typical standard definition of causal set, it's a set, and in the order relation, if you take two elements of the set, then there can only be finitely many elements in between them. But the set itself can be infinite, so you can have infinitely many elements in this causal set. That's so it's discrete, but it's the causal set in that case is discrete, but it's infinite. It could be the ground set of the causal set could be the natural numbers, for example, or the integers. But what I say by that one might be able to get away with just finiteness altogether is that the causal sets that we need to talk about and to describe the universe are only the finite ones. We never need to appeal to the infinite ones. And that's another leap. That's a proposal to say that the universe has a finite past. That every event only has finitely many atomic fundamental events in its past. And I don't know that is the case, but that might be the case.
And to bring the causal set closer to home, so to speak, for our listeners, I think we need to talk about just what the elements of the domain and then the ordering relation are supposed to correspond to. So are the elements of the domain meant to be like these sort of space-time atoms, and then the ordering relation on them is something like a temporal order? Or how yeah, please.
Yeah, exactly. Absolutely. That's exactly right. And those are the right words to use to convey these concepts. So the proposal is that space-time is atomic in the same way that matter is atomic. There are smallest possible events. So, take an event like, I had a tuna sandwich for lunch today. That's an event. And I can divide that up into sub-events. Like, I had a smaller event would be, I took the first bite of my tuna sandwich. And then I could divide that up into even smaller sub-events. So, a particular fraction of time that was in my mouth. Anyway, so you can keep dividing an event up into smaller and smaller sub-events. Altogether, the sub-events make the composed full event. But the proposal that is made in causal sets is that you can't do that forever. In general relativity, you can do that forever. So there's no you can get to arbitrarily small sub-events. But in causal set theory, the proposal is that you can't. There's some at some point you have to stop because you've gotten down to the atomic events.
Mm-hmm. Because in general relativity, as I mentioned earlier, space-time is a continuum and it's
exactly
smooth. Okay.
Exactly. So these atomic events or these space-time atoms, they're the fundamental units of reality, and they are ordered in a temporal sense, where by temporal I just mean that it's an order of precedence. So the ordering is a before and after ordering. So if one event X precedes another event Y, or one space-time atom precedes another space-time atom, then it's just before. The first one is before the second one. And it's a partial ordering because not all of the events are ordered in relation to each other.
So you mentioned two fundamental components to causal set theory, and I saw that there's also a third, and that's that causal sets, they retain the path integral from quantum mechanics. And I think that we should maybe go into each of these three again, just in a little bit more detail, or just connect them back to, well, the theories from which they come in the case of quantum theory and general relativity, and then talk about the discreteness a bit more. But in general relativity, and you've already touched on this, but what is the causal order? It's just that there is always a before and after. Is that what we're retaining?
So in general relativity, space-time is a manifold, differentiable manifold with a Lorentzian metric, and the Lorentzian metric it allows you to categorize paths in space-time as being either time-like, space-like, or null, depending on the metric is a two-tensor. So at every point you can feed a vector into the two slots of the two-tensor, and it spits out a number. And depending on whether the number is positive, negative, or zero, that tells you whether the tangent vector to your curve is well, if it's positive, then it's space-like. If it's negative, it's time-like. And if it's zero, it's null. So a causal curve is one whose tangent vector is nowhere space-like. That means that it could be the path of a material entity like a photon, or a massive particle. So it's a trajectory that some physical entity could follow in space-time. And then the causal order is the relation that is that's derived from that information. So we say that a point of space-time X is to the causal past of a point of space-time Y if there's a future-directed causal curve that goes from X to Y, because X must precede Y, because some material entity could travel from X along this future-directed causal curve to Y, and it could have, if you cause and effect are difficult words to use, but you could have some event at X and it causes some event at Y, and because of that we say that X and Y are causally ordered. So the metric tells you this causal order on all of the space-time points.
Okay, that's really helpful. So, and then moving on, I've done many episodes on quantum theory, so we don't need to dwell on this for too long, but surprisingly, the path integral hasn't really come up yet. So what is it, and how does it connect back to causal sets?
Yeah, that's an interesting and fascinating story. So we think that causal sets will be a quantum theory. I mean, it's a proposal for a theory of quantum, or the basis for a theory of quantum gravity. So it's got to be a quantum theory. But what is quantum theory? That's the
million-dollar question.
Yeah. So there are at least, but there are several different sort of definitions, if you like, of quantum theory. One of which I would call the canonical theory. which is connected to canonical a canonical Hamiltonian framework for classical physics, where you have a background time, you have a Hamiltonian, classical Hamiltonian that's generates time translations of the system, the mechanical system, and there's a way to translate all of that classical technology into a quantum theory based on a Hilbert space, and the Hamiltonian becomes an operator on state vectors in the Hilbert space. And that, yeah, so I call that the canonical or psi framework. And that framework simply won't work for causal sets for all sorts of reasons, including, well, first of all, we don't have a classical theory. One can't really see, we can't see any way to go forward with the idea of there being a Hamiltonian, which is tied to this idea of there being a global time, which just isn't there in a causal set. So it's discrete. So there's Hamiltonian generates continuous time translation. So that won't work either. So there's just nothing about the canonical theory that matches or fits at all with the idea that the fundamental sort of ontological entity is this causal set. So we have to look around for what else is available. I mean, we could come up with some other framework for quantum theory, but what's available today is we already have the path integral. And if you generalize it slightly away from path integral to sum over histories, then it's just in those words, sum over histories, it points to a way forwards for causal sets, because a causal set can be a history. It can be a whole space-time, the whole history of the cosmos. And we just need to be able to sum over causal sets in order to connect with quantum theory. Of course, I'm just brushing all sorts of conceptual questions and issues under the carpet here, but it's sort of in its just heuristic name, sum over histories, it's already announcing itself as being rather compatible with causal set theory. And also that if you think about the path integral in a certain way as an approach to the foundations of quantum theory, rather than just as a calculational tool for calculating, say, the propagator in a canonical theory, then the concepts that it deals with are the same concepts that GR deals with. So the path integral deals with events and it deals with histories, and so does GR. It deals with things that happen in space-time, and it deals with histories, which are completely fine-grained descriptions of a space-time with matter fields in it. So there's a conceptual matchup between the path integral, thought of as a foundation for quantum theory, and a relativistic theory like general relativity. The basic concept, the things you're talking about when you talk about the physical system, are the same. Whereas in the canonical theory, that's just not the case. That even in ordinary quantum mechanics, the things you talk about just are different sorts of things. In a classical theory, you do talk about events in space-time, and in the quantum theory, you're talking about self-adjoint operators. Just the conceptual, or results of measurements, or just different sorts of things. We like to think that the path integral is a useful way to think about foundations of quantum theory, even quite apart from causal sets. So in and of itself, it should be studied and worked on as a different foundation for quantum theories. But for causal sets, we have no choice. There's nothing else on the market for us.
Yeah, that raises some interesting questions. So I was wondering as I was reading about the relation of the path integral to causal sets, whether this meant in so much as causal set theory, which is not quantum field theory. I mean, it's a proposal for quantum gravity, but as you mentioned, it's still quantum mechanical. Whether it, as a theory, can be committed to something like an interpretation of quantum mechanics. For instance, in taking the path integral as primitive, it adopts the sum over histories approach, in which all possible trajectories of a system are equally real. Is that how you see it? I mean, it sort of forces your hand to pick a horse in the foundations of physics debate over quantum theory.
Yeah, a couple of things you said I wouldn't agree with, but overall, yes, the at our current stage of knowledge and understanding, and given what we already know, what we already have in the world of quantum foundations, yeah, I think the structure of causal sets, their discreteness, their inherently space-time aspect, that there's no sense in which a causal set is like something, say, three-dimensional, evolving in time or changing in time, or it simply doesn't have that character at all. So it simply doesn't lend itself to any kind of canonical treatment. It's really inimical to that. So it does. It forces us to take the path integral as the basis for the quantum theory. But I'm not saying that is going to be the case always. It may be that it's just a stepping stone once we understand what quantum causal sets are better. It may be that we can jettison the path integral and talk about the path integral gives you a measure. The path integral is not the thing. It's not telling you about the way the causal set is behaving directly. It's the path integral is the analog of a probability measure. So for example, stochastic processes like Brownian motion, the particle goes on a walk, it has a trajectory in space-time, and the measure of the dynamics is encoded in this measure, but the measure it's not the measure in itself is not the real thing. It's just somewhat mysteriously and obliquely telling the particle what it can and cannot do. So the path integral is like that. It doesn't have the status of being the real thing. That the real thing is something. What is the real thing? That's the question that every approach to the foundations of quantum theory has to answer. And we have the bare bones of an answer, but not the full answer. So the bare bones of the answer is that the real thing in a quantum theory, a path integral quantum theory, is a statement, yes or no, to every possible question. Does such and such an event happen? And in the world, it either happens or it doesn't happen. And the list of all those answers, yes, no, yes, no, 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 yes, no, to all the possible, for every event, you can ask the question, does this event happen or does it or not? And then the answer to all those questions, that's the world. That's the. We like to joke that it's a Wittgensteinian answer. It's everything that is the case.
Well, Now that we've touched on the causal order and the path integral, what is the intuition that motivates taking fundamental discreteness in space-time as so crucial to reconciling quantum theory and general relativity?
Good. The discreteness by itself is something which you can motivate from a pragmatic point of view or from a sort of philosophical point of view. So we touched on the philosophical point of view, but the pragmatic point of view is that it's very difficult to make sense of, to define even the path integral. So if so these things, they're sort of coupled together in this way. They go as a package. They're made for each other somehow. So how do you do calculations in quantum gravity? And the discreteness, and particularly finiteness, of course, makes the question of defining things, defining what you mean, the entities that you want to calculate, a lot easier. So, I mean, the path integral for quantum field theory, famously, it isn't a well-defined mathematical entity, and even in quantum mechanics, it's not a well-defined mathematical entity. So the idea of being able to define it for quantum gravity is rather hair-raising. But if you just say, well, the class of things that we have to sum over is actually finite class, you don't even need to worry about integrals, let alone infinite dimensional integrals, then one can relax about whether or not things are defined, mathematically defined. So and discrete techniques are often used to try to define path integrals as limiting, as the limits of finite of a sequence of more or less discrete entities along the way.
Well,
does that answer your?
It does. I think it's good that there are pragmatic and philosophical dimensions. It makes it easier to wrap my head around the ways in which it's important to the theory of quantum gravity that we've been discussing. But I think before I continue probing the fine details of causal sets, it would be very helpful for both me and our listeners to make this all somehow more concrete and connect it to something in the universe. And one of the ways I've found for getting started in this area with string theory that's most helpful is by talking about black holes and thermodynamics, since these areas are crucial to quantum gravity. And I'm wondering if that seems like the right place to start for making causal sets concrete as well.
Sure. Yeah.
So how do they connect to black holes?
So we have within causal set theory, we kind of have a proposal for what an understanding of the black hole entropy could be. So that's a task which many approaches, as you say, many approaches to quantum gravity have set themselves to try to understand why the entropy of a black hole is proportional to its area, and more specifically is equal to its area in Planck scale units up to some factor of order 1. So what is it? Oh, I should have mentioned actually that result, or that value for the black hole entropy, is another of the reasons to appeal that points towards discreteness, because it suggests that there's something discrete going on at the horizon of a black hole, because it's simply if you imagine tiling the horizon of a black hole with Planck-sized tiles, little squares, 1 Planck length by 1 Planck length, then just counting the number of them gives you the black hole entropy. So
it's like a hint in the universe that was very hard to find. It took us many thousands of years, but
yes.
But that points toward discreteness.
Yes, well, I think we have to confess that it's only a theoretical hint, because no one has measured the entropy of a black hole. So it's not a hint that comes from the laboratory or even the telescope. It's something which, yes, it's on paper. It's a theoretical hint. So, but there's a very strong one that many people take very seriously, and yeah, so it plays the role of phenomenology in quantum gravity for sure. So that's I also probably that's certainly one of the strongest indications that there's something discrete going on in that space-time. There should be some kind of fundamental cutoff at close to the Planck scale. So can causal set? What can causal sets have to say about black hole entropy? So one idea is that, well, the space-time with a black hole in it is the continuum approximation to a causal set, that really the underlying entity, the underlying physical substructure to a black hole space-time is a causal set. So just as the fluid description of a cup of coffee is a continuum description to something fundamentally discrete, which is the description of the molecules of the coffee moving around. We postulate that the space-time of GR, which has this black hole in it, is this black hole space-time, is a continuum approximation to this discrete causal set. Okay, so that's one idea. And then one way forward is to look at that causal set and try to identify within it some part of it, so a sub-causal set, some part of it, which corresponds to the horizon of the black hole and corresponds to it at some moment of time. So when people say the area of the horizon of a black hole, they mean the area of the horizon at a particular time. So we try to identify in the causal set some part of the causal set that corresponds to that horizon. And then we just study that and see, can we say that subcausal set has microstructure? And can we say that it has microstates? Can we count those states in a Boltzmannian way, take the logarithm of the number of those states, and get something which scales like the entropy, like the area? That's the proposal. And so we're doing that. We've made some progress on that. So we can look at a causal set which has Schwarzschild as a good approximation. We can identify we have a proposal for what the sub-causal set is that corresponds to the horizon, and we've proposed certain microstates and counted them, and it does scale in the right way. Where I'm not going to make strong claims at the minute, because what we would want would be that all black hole horizons will have the same. The counting will give you the same exact. It doesn't just have to scale like the area, but it has to scale with the same coefficient. So the ratio between the counting and the area in discreteness units has to be the same number, the same constant for every type of black hole, because that's what the black hole entropy tells us has to happen. So we haven't nailed, but we're approaching the problem of what the microstates are that the black hole entropy counts, in this way in causal set theory.
This notion of the Planck area tiling around the black hole, I think it raises a very natural question, at least for me, about causal sets that has to do with just this discreteness of space. And is there I don't know the right way of putting the question, but is there like a distance, like a fixed distance between space-time atoms, or do these still fluctuate? These distances still fluctuate in a quantum mechanical sense, or I mean, where does the Planck length fit into these really small scales of causal set theory? It's sort of a cluster of questions.
Yes, that's a good cluster of questions. So one thing to stress is that the discreteness of the causal set is space-time discreteness. So I'll say a bit more about what I mean by that, but I want to contrast that with the idea that space is discrete. So it's been a folk wisdom that you can't have discrete space because the Planck length is not a Lorentz invariant concept. So what one means by that is that because of what people call Lorentz contraction, if you have something which is one Planck length long, and an object which is one Planck length long, and you look at that from the frame of reference of someone who's moving with respect to the object, which is just sitting at rest, say, and someone's moving with respect to it, then it will look shorter. And that doesn't make sense if you think of the Planck length as being the shortest possible length. So there's a contradiction that's been pointed to many times, and people say, well, you can't have a shortest length because that's not a Lorentz invariant concept. It doesn't accord with relativity, with special relativity or general relativity. So it's just a no-go. It's a no-go. You can't have discreteness consistent with relativity. But the get out of this no-go result or argument is that the discreteness of a causal set, you can have discreteness so long as that discreteness is at the level of space-time. So instead of having discrete lengths, you have discrete space-time volumes. So the space-time volume, say in 4 dimensions, so our universe. So in 4 dimensions, you have 4-dimensional volume. So that's a 4-dimensional volume would be, for example, a cube of space, 1 centimeter by 1 centimeter by 1 centimeter, that sweeps out a world volume of 1 second long. So that's a 4-dimensional volume of space-time. And that 4-dimensional volume is 1 centimeter by 1 centimeter by 1 centimeter times 1 second. That is 10 to the, so a centimeter is 10 to the 33 roughly Planck lengths. So that's 10 to the 99 for the cube. And then it sweeps out this space-time volume that's 1 second long. And a second is about 10 to the 44 Planck time. So that's 10 to the 143 Planck units of space-time volume, right? That's and the idea of causal sets is that in that volume, that region of space-time, it's a 4-dimensional thing. It has roughly 10 to the 43. It's made of, it's composed of, it comprises roughly 10 to the 43 space-time atoms, these fundamental units of reality, with their order relations between them. That's what that region of space-time is, that volume of space-time. And because it's a volume, that's a Lorentz invariant concept. If someone sweeps by fast in a rocket ship and looks at this space-time volume and measures its space-time volume, according to them, it's the same volume. So volume, space-time volume, is a physical concept. It doesn't depend on what frame of reference you're asking the question in. Length is not a physical concept in the sense of being invariant depending on what under different frames of reference. But space-time volume is invariant. It's physical. It doesn't care whether you're in a rocket ship or not. It's the same. It's the same volume. So the discreteness of, it's important that the discreteness of causal sets is space-time discreteness, not spatial discreteness. That's one thing to say. So what was your? I think that was a preamble to answering a question that you asked, which I've now forgotten.
No, I think that you pretty much covered the question, but well, it was a jumble of questions. But I was asking about, let's see, I was asking about the minimal length between space-time atoms. I think that what you might not have answered, what minimal distance between space-time atoms. What I think you might not have answered was whether these distances fluctuate in a quantum mechanical sense.
Right. So in the quantum theory, that is what I think one would have to rephrase the question slightly, and I don't know how to rephrase it because I don't. Yeah, the quantum theory is the frontier. It's the major frontier of beyond which there are unknowns. But in terms of a single causal set, the idea of fluctuating distances, it doesn't really come into play because the scale of the discreteness is just the Planck scale. So in order to ask about fluctuations in space-time, you have to address the question of the relationship between the continuum approximation and the discrete entity. So maybe I can work up to an answer to your question by describing how the continuum approximation is related to the causal set. So that was actually inherent in my answer to the question about the black hole. How are we dealing with, what kind of causal set are we looking at when we say we're probing a causal set that has Schwarzschild spacetime as a good approximation to it. So the discrete continuum correspondence for causal sets is that a spacetime is a good approximation. A spacetime, let's call it M for manifold. M is a good approximation to a causal set C if C can be faithfully embedded in M. So C is a discrete thing, so there can't be a bijection between them because C is discrete and M is a continuum, so that's not going to work. But you can embed the elements of C into M, and it has to be faithfully embedded, meaning that the order relation between the elements of C, the causal order of the causal set, has to accord with the light cone structure. So if A precedes B in the causal set, then the embedded point A has to be in the past light cone of B. So the embedding has to respect the causal order and the space-time causal order, and it has to be uniform in the volume measure. So the number of causal set elements embedded in any particular region, large enough region of the space-time, has to be approximately equal to the volume of that space-time region in fundamental Planckian units. So that discrete continuum correspondence, that holds the physics of how we're going to recover things that we know how to talk about, how to interpret, like things in space-time in terms of the causal set. It's via this discrete continuum correspondence, via this embedding.
Clarifying the discreteness of space-time from the discreteness of space is it's crucial and it's really helpful. But with the time we have left, I'd like to talk about some of the particularly neat features and consequences of causal set theory. And you just said that the Planck length isn't a Lorentz invariant conception. We talked about how volume, on the other hand, is invariant. But Lorentz invariance, or Lorentz symmetry, as it's also known, is quite important to causal sets. But the term hasn't come up before on the show, actually, at all. And this is more a conceptual and a terminological question. But could you maybe just briefly say specifically what it is? And this, I think, is the crucial portion, how it connects to causal set theory and phenomenology.
Good. So Lorentz invariance it's an approximate symmetry of general relativity. So it's not an exact symmetry. It's approximate in the following sense, that it says that, so in general relativity, if you were to consider a small laboratory, say on a rocket ship, and you do an experiment, any kind of experiment of any sort of physics at all. So it could be particle physics, it could involve details. I mean, you're not going to fit the whole of CERN onto a small rocket ship, but something involving, radioactivity or anything involving gravity, falling things, or anything. So the idea is that any kind of physics, and you do that, and the experiment takes a certain amount of time that's not too long. Okay. Then you cannot tell whether or not that rocket ship is in motion. That's or uniform motion, let's say. So, of course, you can tell if you look out the windows of the rocket ship, but that's against the rules of the game. You're not allowed. So, in relativity, you're not allowed to look out of the windows of the rocket ship. But you can't tell. The physics just looks the same. The predictions that you make are using the same physics, and it's the same rules the same physics that you would use in special relativity when there's no gravity. So that it's an approximate symmetry because it's not true for if the rocket ship's very large or the experiment lasts for a long time. Then you can tell that you're not that there's a non-uniform gravitational field, for example. So the physics is then different from the physics in special relativity. So it's an approximate symmetry, only applies for small labs for a short length of time, but we have no evidence that symmetry is broken. There's no evidence that there's a preferred frame in our space-time, and there's plenty of so the experimental bounds on the amount of violation of Lorentz invariance that is possible get smaller and smaller as we do more and more experiments.
Great. And another thing that I wanted to make sure that we got to is at the beginning of our conversation when we were talking about Einstein-Rosen bridges, EPR came up. And in the context of EPR, we were talking about non-locality and wormholes. But non-locality is one of the more unintuitive findings in quantum mechanics. And as we already said, it was something that Einstein protested vehemently. And am I right that causal sets side with QM on the matter rather than Einstein, and that they're resolutely non-local?
Right. So the non-locality that Einstein that perturbed him, I think, is something we might want to call acausality, where this spooky action at a distance that you referred to is action at a distance in space, so that something over here can instantaneously, something that happens over here can instantaneously affect something that happens over here in space. So and that's superluminal, because this shouldn't be able to affect this, because there's no time for light to have traveled from here to here. So that's the sort of non-locality that Einstein seemed to be perturbed about. And I think he had in mind the idea that the wave function was a real thing, and that if you consider the wave function to be a real thing, then indeed, if you do stuff over here, then it changes the wave function over there. So that was what he was bothered by, or didn't like at all. So I think we would call that acausality, because it's propagation outside the future light cone. So it's not causal. It's not relativistically causal. You've got yeah. So causal sets are resolutely non-local, but they're also causal. So it's non-local but causal, which is different. So the non-locality of causal sets is non-local in time. So something that happens here can influence something that happens in its future, still in the causal future, but at a great distance, so to speak, in time, or in space-time, at a great distance in space-time, where distance, you see that it's a slippery term. So it's non-local in the sense that it jumps over it can jump over some region of space-time. But distance it's slippery, because the time, the proper time, the physical time between the two space-time atoms is actually really small. That's this peculiar thing about Lorentzian geometry. So the trajectory of a photon in space-time is a line. I'm now talking about the continuum, so nothing to do with causal sets at the moment. So the trajectory of a photon that travels at the speed of light is a line in space-time, and along that line, there is zero distance between any of the points on that line. So that's this astonishing, amazing, fall-off-your-chair feature of the geometry, Lorentzian geometry. There are these special directions, the null directions, or the light-like directions, in which there is no distance between the points in those directions. So when we see a photon that was produced at the surface of last scattering, it is as fresh. It took no time at all along its trajectory to reach us.
That captures the idea that time doesn't pass for photons.
Right. That phrase is referring to that mathematical fact that there's no. And then if you think about something that travels on a world line in space-time that's very, very, very close to that to that light-like null trajectory, to the photon trajectory, just it's not light-like, but very close to it, then you could, in some sense, the two events connected by that line are very far apart from each other, but they're also only one unit of Planck time away from each other. So that you have to rejig your concept of distance in a Lorentzian space-time, and causal sets capture that. So there are nearest neighbor space-time atoms with no space-time atoms between them. So they're nearest neighbors. But one can be at the beginning of the universe just after the Big Bang, and one can be here and now. And they're very it's a non-local connection across space-time, but it's completely causal. So there's no jumping outside the light cone.
No, that makes complete sense. I mean, they're next to each other. I mean, it's confusing, but it makes sense.
Yes.
I mean, when you take into account this notion of time not passing for a photon, that's what puts the ideas together for me. So one other dimension of causal set theory that I wanted to make sure we touched on, particularly because it was so surprising to me, was the connection to consciousness. Because aside from Penrose's writings on quantum nanotubules, I hadn't seen that much from serious physicists about the problem. So the hard problem of consciousness, for our listeners who aren't familiar with it or haven't heard episodes of the show that connect to it, can be contrasted with the easy problem of consciousness, which is sort of understanding maybe how the brain, what's going on in the brain that gives rise to experience. But the hard problem of consciousness is understanding just how something physical that doesn't seem like it should be the subject of qualitative feelings, like how this block of matter that is my brain has feelings and experiences of the world. How are we supposed to explain that? And what I understand is that causal set theory may have something to say about this.
That's what I am proposing. I can't say that any of my colleagues working on causal sets endorse what I am now going to say. So it's not something there's a consensus on at all in the community of workers on causal sets. So it's just something that I've proposed, and I'm happy to get feedback on. But the idea is that there are two types of thing in the world. So I hesitate to call it a dualism because of the baggage that comes along with that term. So it's not like that, but there are two types of thing, but they're intimately connected, right? So, and the two types of thing are the atoms of space-time that every space-time is made of, and the coming into being of those atoms of space-time, or the becoming of them, or the birth of them. And the idea is that the dynamics of causal sets is a process of the coming into being of the space-time atoms, and that process is a crucial part of, and is just as much a part of, and just as physical as the space-time atoms themselves. So, but they're obviously a different type of thing. So I sometimes use the slogan, the birth of a baby is not a baby. So the birth of a space-time atom, its coming into being, is not a space-time atom. They're different. They're just different types of thing, but they're intimately connected, because without the birth, there is no space-time atom. So, and the space-time atom is what's being born in the process. So the process is the birth. So people sometimes say how, and the idea is that it's the process that correlates with conscious experience. That's it. It's not the space-time atoms. It's not any particular thing. It's not any particular substance. It's not any particular event that corresponds with the actual having of the experience. It's the process. So the seat of consciousness is this process. And then so I've written a paper on it, and in the paper I strengthen this proposal by making connections between qualities of conscious experience and properties of the birth process. in causal set theory and say that you can, there are matches that you can make between the two things. So if you say, how does conscious experience, how does it interact with matter? That's like saying, how does the birth of a baby interact with a baby? Interaction is the wrong term. It's
yeah. So the seed of consciousness, as you put it, it's the process of the birth of space-time atoms, or is the birth of space-time atoms just the root of the experience of the passage of time? Or is it both of these things?
It's difficult to say because people mean different things. These people have thought about these things for much longer than me. Probably you, since you have a philosophical background and training, but they mean things, and I don't know what people mean by them. But I think the quality. Somehow it's the quality of conscious experience that that the hard problem pertains to. The fact that it's live and inexorable and somehow uncommunicable. You can't experience what I'm experiencing, and I can't experience what you're experiencing. So, and the proposal is that it's our experience of the passage of time, which is what the hard problem is to do with. It's that aspect of our consciousness which is hard. That's
maybe what I should drill into then is the relationship of causal sets to the passage of time, and how does it. So this moving spotlight, I guess, is sort of the metaphor or the image that often comes up in discussions of the passage of time when we're wondering what distinguishes the present from the past and the future, especially if the past and the future, and this is kind of vague, are equally real. It's this spotlight that's tracking each successive moment. Something is in the now when it's in the spotlight. And the question that I have is, why? So does general relativity not leave room for this spotlight, but causal sets do? There's sort of a mechanism for the spotlight. That's one of the things that distinguishes the two theories.
Yes, in a sense that the process is the spotlight, but the process is this birth. So in the spotlight, one has the way it's described, the way I read it is that the whole space-time, the whole block already exists, and it's just that certain bits are illuminated. But the whole thing is there, right? Past, present, and future. Whereas in the causal set process, the birth process, fits more, but not quite. It fits more with the idea of a growing block. That the past is real, but the future doesn't, is open. And the present is the process. I tried that metaphor out in a paper, and the reviewer really didn't like it, so I took it out. But I can try it out on you.
A growing space-time worm.
The present is the process, but the thing about the causal set process is that you cannot view it from the outside in an objective way because it's partially ordered. So this is something which I've tried to express to various audiences. So let me try it here. So these space-time atoms are partially ordered. So you might have the the set of space-time atoms that comprises an event, like it could be a neural event, some event that takes place in the brain. It takes 10 nanoseconds or some time, and it's the neuron is maybe a few millimeters long or something. Anyway, so it has some space-time volume in your brain, let's say, and it's made of space-time atoms. And those space-time atoms, they're partially ordered, not totally ordered. So some of the space-time atoms have no order relation between them. There's no fact of the matter about whether A happens before B or B happens before A. They just don't happen in any order. But if you try to put yourself outside the physics and look at it from the outside, so sort of run a movie of it in your brain, just imagine the space-time atoms being born, then you automatically, in your mind, put on that process a total order. You will have to imagine either atom A coming into being before B or B coming into being before A. That you can't imagine the process, this birth process, in a partial order. So there's no way to have an external view of this growing block process. The only way you can have a view of it, and this is my argument, is from within. If you're part of the physics, you can have a view of the process that's objective, and that is conscious experience. So your conscious experience is an internal view, internal objective view of this partially ordered process of the birth of space-time atoms. It's not something you can view from the outside. And that's something which I use to connect aspects of the debate about the hard problem with this proposal. That's, for me, that unlocks, or it illuminates the argument from knowledge, for example. That's for me.
When you say that the future isn't, so in your picture, it's this growing, I'll just use my words, it's this growing space-time worm or this growing block. You say that the future isn't real. And that makes sense to me because the space-time atoms that will eventually comprise the future, they haven't been born yet, so they're not real. I understand why the present is real because we're in it, and the space-time atoms are born in each now. I want to better understand why you still take the past to be real, and this is maybe it's not it's a very used story, but you can't kick the past. I can't kick Julius Caesar many years ago. The way that I can pet my cat or something that's real right now. And I'm wondering if this maybe brings us back to non-locality, and maybe the reason that these space-time atoms in the past are still real is that they're still having non-local interactions with the present. With
yes,
the now.
Exactly. That's exactly the reason why they're still there. Because, yes, you can't kick Julius Caesar, but Julius Caesar can still perhaps not kick you, but kick something that hasn't happened yet, but in the future that's one Planck unit of proper time away from him.
Right. Through the photons that reflected off of it. Okay.
Right. The potential for causal efficacy, or what words to use, but they still have potency. They're still able to have causal effects, no matter how far back in the past they are, because of the non-locality. Exactly. Yes. Exactly right.
Perfect. Well, since I got that right, that's a great note on which to end. This has been really, really fun. I mean, causal sets are a totally new world for me, and I like to be collecting these theories of quantum gravity. It's a very fun area to talk about. So thank you so much, Fay, for joining me and sharing your expertise on this subject.
No, thank you, Robinson. It's been a lot of fun. Talking about causal sets makes me happy. So thank you.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Erhardt.